So my name is Ronan Collins. I'm originally from Ireland. I left Ireland some 20 years ago to move to, of all places, Hong Kong. I ran a company in Hong Kong called IntelliBuild, where we ran building information modeling management services for engineering firms, architectural practices, and major contracting organizations. Some 12 years ago, I met my beloved wife, who's actually from Malaysia. And we returned to Malaysia about 5 years ago. Since then, I've been working with the MRT, AECOM, and most recently with Gamuda Construction. And I'm going to show you some of the innovations that we brought to bear on the MRT project in Kuala Lumpur. So this is a very overused image by now. These are two of our surveyors. And the important thing to note here is we've actually trained the surveying team to operate the drones, so that we don't have a special drone team by any stretch of the imagination. These are competent, experienced surveyors. You can see here Mr. Fai is actually operating the drone, and you can see we have a spotter. And I'm going to explain the roles of these two different people in the operation of the drones. And obviously, most of you recognize the landmark in the background as being the Petronas Towers, or as we call it in Malaysia, KLCC. So the project that this was started on and was the kind of instigator for using drones for Gamuda was the MRT project in Kuala Lumpur. So we call it MRT2 or the SSP line, depending on who you speak to. And I was specifically responsible for the BIM management for the underground section. So this is a 3D photogrammic model. So the first kind of term to be understood is this notion of photogrammetry or photogrammic. Photogrammetry is a process where you take a standard photograph, preferably high resolution. The photograph can be captured either by drone, it can be captured by a fixed-wing aircraft, so normal flight, and it can actually be captured by handheld cameras. So there's a number of ways of capturing the photograph. So long as the photograph has got a location key to it, so long as we know where the photograph was taken, we can then use all of the photographs to create these 3D surfaces. So what you're looking at here is actually a 3D mesh of the entire KL urban environment where we're actually doing the tunnel construction. So this little video shows you a very good example of how you can build a 3D model of a city or an environment using a combination, in our case, of drone footage and aerial photography. So there you can see the Petronas Towers in the foreground. And the purpose of this little video is to show you the locations of all the stations in the built-up environment in Kuala Lumpur. So we have been flying around and above the stations and the surrounding areas over the period of 2 or 3 years, collecting all the photographs, collecting all the information, and building this reference model. And we also got help from one of our service providers who had done broader surveys and had the fixed-wing aircraft photography as well, which we combined together. So this is a very good way of explaining to the public, to the contractors, to the engineers, to the client, where their project is in a 3D environment. So that's the whole of KL. So let me give you some examples of how we actually generate these 3D surface models. And in our case, we're using a software called Context Capture, which is a tool available from Bentley. The Context Capture software can absorb and use photographs. It can absorb LiDAR information. It can take in terrestrial laser scanners. It can take in handheld photographs. And it then runs the photogrammetry algorithms to generate the 3D meshes. So when we talk about photo capture or photogrammetry, essentially, we fly the drone over the construction site, typically 80 to 100 meters above the construction site level, and we take overlapping photographs. Now, the overlapping photographs is critical. So you need to make sure that each image is 70% of the previous image. So you can see here as I progress through this sequence of images, it's continuously overlapping the images. And the reason for this is that the software is looking for particular pixels or particular aspects, and it needs them in 3 or 4 or 5 positions to create an accurate 3D position of where it is. So this is why we do these overlapping photographs. You can see from the image data that these are very large files. These examples are actually from 2017, so this is, shows you how long we've been doing this. So you can see they're 5,000 pixels by 3,500 pixels, so very high resolution. And to give you an example of how high a resolution, if I zoom into one, if you see the little yellow box, that's myself and my colleague Nick Moorcock, and this is actually a set of images that we took. I think this was the second or third trial run that we did. So this is a good example of how we actually operate. We're standing in the shade of the excavator because in Malaysia it's 35 degrees, but one of us is operating the software to operate the drone, and the other person is actually operating or monitoring the drone in flight. So if you do this on your own, it's very difficult to keep an eye on the software, keep an eye on the drone, keep an eye on the construction site, keep an eye out for activities around you. So we have a policy that every operation that we do with the drones involves two people. One person operating the software and the other person is a spotter to make sure everything is safe and under control. So this little video, if I get this to work, shows you what the software looks like on a mobile device or an iPad. So we use iPads typically for this operation. So we actually pre-plan every flight. So here you can see a simulation of a drone following a pre-planned path. So the planning of the path makes sure that we achieve the 70% overlap of the images. So basically we make sure that we can actually fly the path and that we capture enough images for the area that we actually want to survey and create a 3D surface model from. So this would take typically 15 to 20 minutes on one battery, and we can cover quite a large area of the site. So once we've worked out for each individual site the flight paths, they're saved and they can be reused over and over and over again. Go to the next slide. So just for a bit of fun, this is actually a drone taking a video of a drone following a path. So we've been doing these kind of presentations to teach people how to do the drone. So we've been using one drone to video another drone. So here you can see a survey taking place. And if you know how to do it, you can actually set the drones up to fly it close to excavations, so you can get better information about what's beneath the ground level. This is not a radar, so it only works on visuals. But when you have these kind of open excavations, very often you need to get a bit closer to the excavation wall to get a bit more detail from the photographs to be able to build a more accurate 3D model of the excavation. So it takes a bit of practice in terms of getting the right information from the photographs, but once you've got it figured out, you can create some very detailed models. Now, one thing that people don't understand or are not familiar with is this concept of ground control points. In order for the surveyors to be able to create a 3D surface model, which is actually based on the National Coordinate System, which in our case is the Cassini grid in Kuala Lumpur, you have to make sure that you can take accurate ground control points. So here you can see the surveyor is setting up a ground control point and he's measuring the GPS coordinates of that ground control point. And if I play the video again, you'll notice that we've got a red and white map. So basically that red and white map will turn up in the photographs in the context capture mesh. And then we will set that ground control point as per the coordinates of this particular survey station. So what we've learned in doing this is that for a typical site area, you might need 5 or 6 ground control points in the photographic survey to get an accurate position of the mesh in terms of real world coordinates. If you don't use ground control points, you can position the mesh by eye, but it's not very accurate. So again, we recommend that if you're doing surveys with drones to create these meshes to be able to use them for other purposes, you need to have ground control points. So the key issue working in Malaysia, and I think this is true for most countries, is that you actually have to put a lot of effort into the planning and operation of the drones. It's not simply a case of charging it, getting in your car and going to site and flying the thing. That's actually not a very clever way of doing it. So the more planning and the more preparation you put in, the more successful your drone operations are going to be. So before we do any flights, we have a pre-flight discussion or meeting and we say, why are we flying the drone? What's the purpose? Are we doing it to survey something? Are we doing it to record something? Are we doing it to create a mesh? We have an objective in mind as to why we're operating the drone. And then once we understand what we're doing and once we understand where we're going to be flying, in Malaysia we then have to get 2 permits. One is from JUPEM and one is from CAM. JUPEM is a survey permit. There's a law in Malaysia that prohibits the use of aerial drones, helicopters and planes for photography without permission. So we have to get permission to fly the drone and capture photographs. And CAM is the airport authority. So we basically have to notify the air traffic control team that we're operating a drone in the airspace in and around Kuala Lumpur or wherever we're operating. So we have to notify 2 authorities and we need to make sure we've got the right certificates in place to do that. We then make sure that every flight operation involves 2 people, a pilot and a spotter. So we then have a system for logging all those flights. So it's worth remembering that the photographs may be taken for one purpose on one day, but by keeping a record of those photographs and by keeping a record of the model, we can actually use those photographs in the future for potentially other uses. So future projects, future developments, or going back and doing comparisons. And the other important thing is by keeping a log, we actually maintain a diary for the drone. So we need to make sure we know how many hours have been logged for each drone. We need to make sure that if there's any issues with the drone, they get tracked in a very similar way to maintaining any asset. So we make sure that there's a pre-flight check on the drone to make sure there's nothing wrong with the batteries, with the propellers, with the motors, with the camera. And if after the flight, if there's any issues, that they get logged and then they get resolved. So the maintenance of the drones is critical. We don't want one of these things falling out of the sky in the middle of an operation. So these are the kind of pre-planning and checklists that we go through. So this is a good example of some of the planning. So in this example, we're planning out a flight path for a future project. This is for a rail alignment in actually in Penang. So you can see here that we've mapped out where we want to survey. You can see the alignment that we're looking at as a potential alignment. And then we've provided all the coordinate points of the actual boundary that we're going to fly. So that information is provided to the authorities. And we say, we're going to fly this path on the 6th of November. Please grant us permission to do so. And more often than not, we get permission. One of the things you'll notice here is that we actually identify the local police station. So very often we will actually go to the police station locally and tell them what we're doing. We'll give them a copy of the permits and we'll say, look, today we're going to be out flying the drones. Just in case anybody sees it or somebody reports it, you need to know that we're out there flying the drones and what we're doing. And it's just a courtesy to the police that we actually tell them what's happening. So the first thing is safety. So safety is a priority for all of Gamuda engineering operations, whether it's flying drones or construction. And in this example, it's not just about making sure you've got a fancy red and white barrier. Safety also involves checking the device before you fly it. So make sure that all the propellers are properly attached, make sure they're not cracked or scratched, make sure that the legs of the drone are properly built, there's no cracks. And then we operate the drone from a safe designated area away from normal construction operations. So you'll see here where they're operating the drone, there's no active operations in that position. There's no nearby cranes, there's no nearby excavators, there's nothing happening in that area. And it provides a safe area for the drone to take off and it provides a safe area for the drone to return to. So again, re-emphasizing the point, so we actually got vests made for the survey team so we could identify who was who. So this is the drone pilot. He's responsible for the operation of the drone at all times. And the actual more important guy is the drone spotter. And the drone spotter is you'll see him here in a second turning around, he's got a radio. He is in contact with the site safety manager, the site safety supervisor. He's standing local to the drone operator and he's keeping an eye on the position of the drone. He's keeping an eye on surrounding activities. He's making sure that the drone's not going to crash into a crane or anything else. And if there is any incidents, he will instruct the pilot to bring the drone back to the safe landing spot immediately. So again, all part of a safe policy that we operate these drones as safely and as smartly as we possibly can. So now I'm going to show you what we use the data for once we've done the drone surveys. So in this example, I'm going to show you an orthophotographic map. So you can see in the bottom right corner one of the stations, Bandar Malaysia, and in the top left corner you're going to see Chan Sao Lin. So these are two stations along the alignment, and there's a very simple S-curve in the TBM drive between the two locations. This TBM drive is crossing over a major highway interchange on the outskirts of KL City. So this is a very sensitive area and had to be monitored very carefully. So an orthophoto is generated automatically by the software based on the 3D model and the photographs are taken. So you can generate a true orthographic image of any site by flying the drones and using the context capture software to create the orthographic photo. It is dimensionally accurate and it is a true orthogonal image. So you will not see the slope in the walls. You will see basically the verticality of the elements, and it is a true two-dimensional image. So you can bring this into CAD, you can bring this into Revit, you can bring this into Navisworks, you can use it for backgrounds. It's a very useful 2D information. And this is the Chan Sao Lin image. And what we've been doing is we've actually been taking these images and using them in GIS. These are more accurate than the available information on most GIS platforms. So this gives us a much more accurate representation of the construction site at a given point in time. So we prefer to use these ortho photographs in the GIS. And just to give you an example, why this is important. This is an image from Google Maps or Google Earth, and you can see the tilt of the buildings. This image was taken by a satellite, so it's obviously going to have a very high resolution in terms of its distance. If I overlay a typical orthophotographic image or ortho image, you'll see there's a lot more information, a lot more detail, but more importantly, the buildings are actually vertical. So they can actually be correlated with cadastral maps, they can be correlated with proper street maps, survey maps, and we can map out the TBM with great accuracy in terms of its projected path and actually its final path as it passes underneath particular properties or particular road crossings, etc., etc. So using these ortho photographs is a very good way of being able to combine different sets of information. Now I'm going to show you something a little bit unique in terms of what we've been doing with some of these meshes. So this is a traditional time lapse of a construction project. So this is the TBM launches for that same section of tunnels from Bandar Malaysia to Chan Sao Lin. That's from a fixed camera position. So we cannot use those images to build 3D models. It's not just physically impossible. We would need hundreds of cameras to be able to do that. So what we've done instead is we've flown over the site on a 2-week or 3-week interval, and then we've created a 3D mesh for each period of time. So every time we've done a survey, we've created a mesh of that point in time. And what's happening here is that using the actual photogrammetry software, I've created this kind of orbiting time lapse, but it's actually a 3D mesh. So I can actually look at the sequence of construction across the site in 3D. So I can compare this month's progress to the previous month's progress. I can compare the amount of material on site this time to the amount of material on site last time. And in terms of a wow factor for presenting to clients, because it's a 3D mesh, we can zoom into certain areas, we can look at them different angles, and we can go through the cycle. So this is basically a time-lapse 3D survey of the construction site. And as it gets to the end, you can see that the TBMs are actually in position for the second launch to go south into Bandar Malaysia South and onto the actual portal. So I'm going to spend a bit more time looking at Chan Sao Lin and give you some good examples of how we use these models. So this is basically the level of detail that you can see in these photogrammic models. So you can see the TBM after the breakthrough. You can see the shuttering for the formwork. You can see there's a couple of waves and a couple of kind of blemishes in the model, but for all intents and purposes, it's pretty accurate. And if I show you the actual mesh, this is the mesh that's created from the photogrammetry process. So it's not perfect, it's not ideal, but it is reasonably accurate for our purposes, and it's reasonably accurate to within 50 millimeters. So here you can make out the position of the permanent wall, you can make out the TBM, you can make out the kind of surface mesh for the formwork, and you can kind of make out the position of the permanent wall on the other side. So we can take these meshes, and because we've used ground control points, because we've done this accurately, we can then link this in using the actual project coordinates to the BIM system. So in this example, we've taken the surface mesh into Navisworks, and we've been able to overlay that with the actual designed permanent works. So you can see the base slab, you can see the vertical slabs for the station, and you can tell that it's not 100% perfect, but it's pretty close. It's certainly within tolerance that we've built the permanent works in the right position, which is always a good sign. So it is possible to link the building information models with the survey meshes and make use of them. So just to show you another example of this, this is a 4D sequence that was done in Navisworks Timeliner to show the construction sequence for the same station. So this is the slab pour sequence for Chan Sao Lin Station. And just to show you an example, we do all these stations with 4D. We model out all the stations in 4D. But what we also discovered is we can actually use the same time-lapse basic concept with these models. So again, this is a fixed time-lapse position camera from that same site. So here you can see the excavation sequence. This is an open excavation. There's a rock face here which has been retained, so it's a very safe way of construction. Here you can see the construction of the base slab, and then upon completion of the base slab, you'll see the wall forms going up, and eventually you'll see the TBM arriving. Here's what it looks like when you do this using a combination of photogrammetry and BIM. So we have a 3D mesh of that site excavation. We can cut a section through it. So here you can see a long section to the station. We've got a reference in terms of what we're building ultimately. So that's the base slab. So I've talked about the positioning of the mesh. The other thing about the mesh is that they're very accurate. So we can use the mesh for measuring distance. So you can take linear information off the mesh. And you can also use it, more importantly, for volume calculations. So in this example, get this to play. So what we're doing here, this is me just basically doing a demonstration, but essentially we're using the context capture tools, and you can map out a boundary that you want to measure the volume for the mesh. So what we're doing here is basically tagging the corners of the excavation, and what we're trying to do is work out, in theory, if we wanted to build a platform at a certain level, how much material would we need to excavate and how much material would we need to fill to create that platform. So I've created the boundary, and then I use the mesh and I set it to a certain sampling distance, so in this case 3/4 of a meter, and it then tells me from the mesh how many meters are above and below, and it tells me that I need a certain amount of fill and a certain amount of cut. So the cut is in yellow and the fill is in green. So we've only spent an hour on site with the drones, but now we can actually do a very detailed volume calculation, And while it's not millimeter accurate, it is accurate to within certainly within half a meter in terms of the density or the volume. So it's accurate enough for the purpose of us doing quick surveys and quick measurements. So we can use the mesh to quantify material on site. We can use the mesh to quantify spoil. We can use the mesh to quantify excavation complete. And we can even use the mesh to generate drawings. So I'm going to show you another example where, and this is a highway project, so we're constructing a highway. So we've flown along the alignment of the highway, and we've, in this case, taken the ortho photograph, overlaid it on the actual CAD file showing where the actual plan is for the construction of the highway. And we've been using the drones to monitor the site fill and the site excavation. So typically, you will get these kind of record drawings which the surveyors produce, but they do that by going out with total stations and staffs and spending hours and hours and hours over days and days and days collecting the same information. We're able to do this directly from the mesh. So we can actually go out and survey the site over a matter of hours, convert the photographs into a mesh, and then convert that mesh into a CAD file, and then we can cut that CAD file. So we can actually measure out with great accuracy the cut volumes, the fill volumes, the cumulative volumes, and ultimately the net volumes. And we can do that very quickly. The other use that we've got for the drones is in terms of safety. We've used the drones in a number of examples, but this one I'm going to show you is a good example. So we had a shotcrete wall failure due to water ingress, and you can see here there's some large chunks of concrete. So we, instead of sending in staff and surveyors to see what's going on, we send in the drones. And again, you're looking at a 3D mesh from the photography taken by the drone. So this mesh we can measure. We can measure the size of these rocks. We can estimate the weight of these elements. We can check for where there's potentially unstable, and we can work out a plan for resolving this issue on site. So the drones are a very good tool from a safety perspective by using them. Another example is surveying for the purpose of confirming as-built information, or in this case, confirming that the as-built information is not correct. So here you can see an excavation at one of the stations in the middle of the city. You can see in the middle of the image a concrete wall, and this is actually a TBM launch location. So we're going to set up a TBM, we're going to drive it out through that wall, and we're going to drive underneath this old building. And we were given a set of plans, but the plans didn't tally what we were seeing on site. So we wanted to survey this building, so we used the drones to survey the building. We had a set of as-built drawings, but we knew they weren't correct. And we were particularly concerned about one area where on the drawings there was no major structure, but the building was obviously much bigger and much more substantial. So we took the drones, we surveyed the site. You can see the site is in the bottom corner. You can see the building of interest is in the top. And then what we did was basically zoomed into the area of concern, and we identified that this structure was not on the record plans. And then we were able to use the drone survey model and these images to actually build out a structural model that we were able to use for settlement analysis and risk assessments. So we were able to mock up basically what we thought the structure was, and this structure is actually over the top of the tunnel excavation. So this is part of our risk assessment, risk modeling exercise. So we use the drones as a survey tool rather than clambering around the building and trying to get access to roofs and everything else. So it allows us to do these kind of surveys. So that's how we're using the drones to create tools for BIM and for 3D modeling. What we also wanted to do was make this information available to the entire project team. So on the project, we're using ArcGIS as a platform for delivering geographical information. So that could be map information, tunneling information, borehole logs, etc., etc. One of our team, Tony Joseph, is a GIS specialist, and he was able to work out a process where we could convert the mesh that comes from the drone into a web-based delivery across the GIS platform. So you could use GIS to access the information. So let me show you how that works. So this is the ArcGIS platform. This is a web-based platform, so you just access this through a browser. You don't need any particular software. And this is the 3D mesh. This is again Chancel in station. And this is the mesh. You can see it loading up the background. And we also have input the Revit mesh. So we've got a mesh from Revit for the structure, and we've got the photogrammetry mesh. So if you have access to the GIS platform, you can go to any of the construction sites. You can open up and look at the current or the latest survey information and the latest BIM or digital engineering information, and you can overlay the two together in this GIS environment. So you can actually start to study what progress has been made on site and what work has left to be complete. And this has been a very powerful tool because the project is so large, it's physically impossible to visit all the sites on a regular basis. But it is actually very beneficial for people to be able to look at these models. And the other thing that's important to recognize is that a lot of the design teams are not all based in Malaysia. So we have designers that are operating in Singapore, they're operating in Hong Kong, they've got staff working in the Philippines, in India, in Taiwan. By giving them these surface models, it gives them the chance to review what's happening on site and identify any particular issues or particular concerns, and make sure that the team are all aligned. So making this information available online is actually very, very beneficial. And then just for a bit of fun, when we were doing the tunneling activities, this is actually a video that I captured from our Facebook feed. So we used a drone and we actually ran a video. And this is the TBM, this is the first TBM breakthrough. So this is the actual first TBM drive breakthrough. We've been working on this project for 4 years. And while this goes back to kind of late 2018, it was a great successful milestone for the company to actually make sure that we deliver the first tunnel successfully. But to see that image captured by drone and to see the drone feeding the video directly to social media channels that the public can watch was unique. So for those of you who don't know, if you have a DJI drone, you can make them web enabled and you can live stream the video from them. And we don't recommend it on a regular basis, but in terms of showing unique opportunities or showcasing unique stages in a construction project, it is something that's good fun to do. So as we get towards the end, and hopefully there's going to be a few questions about this process, I just want to carry out a couple of, give you a couple of examples of how we see this going forward. So we've learned how to use the drones to capture the meshes. We've learned how to use them to interact with models, how to put it on GIS, and we've used them for things like safety reviews, quantification, etc. We're still understanding what we can do. So now we've set out to do, we've mapped out what we can do with future projects. So we understand that the drones give us a much better level of inspection. So in theory, if we flew the drone on a daily basis, we'd have probably very, very powerful records of the site at every stage. We don't think that's necessary, but if we do fly every week, we'll have a very good record of the progress of site over a long period of time. If the drones become more efficient in terms of their battery life, we could actually use them for key traffic analysis. So particularly for major operations in and around key areas. So we may use the models to plan out traffic activities. We may use the models to plan out traffic diversions. And we may even use the drones to monitor traffic at certain times. So we see there's an opportunity around traffic management. And then obviously for updating communication to the clients, to the public, this notion of being able to take the meshes, make them available on a GIS platform, make them available to the web. It's a good way for people to see what's happening in the site and make the client at least aware, and potentially the public, of what's happening in terms of construction projects. So these are some of the uses that we see going forward. The important thing is that we're committed to training people, and particularly our surveying team and our engineering team. So we've trained now over 30 people. They're now certified drone pilots and spotters. You can see how accurate the information is and how quickly it's done. In terms of surveying, we're seeing productivity gains of the magnitude of 30 to 50x. And the reason we're seeing that is that the amount of data that can be derived from an image and the amount of information in terms of distances, volumes, the ability to overlay with other information, the ability to incorporate it with cadastral information, to be able to capture that much of information with a survey team would take 30 times the amount of effort. So drones have completely transformed our ability to capture information. They don't completely replace surveyors because we can't use them for setting out. We can't use them for specific tasks when it comes to construction. But in terms of recording and actually doing general survey, they're very, very powerful. And as I say, we're continuing to find innovative ways to use drones. And obviously, hopefully in the Q&A, we'll find out how other people have used drones in their business if they've been using them so far. So that's the end of the presentation. And I think we'll hand over and do a Q&A.